Okay, so we are going to do, we're going to look at course outline questions, and there's a whole bunch here that we're going to go through. Okay, so if we don't finish today, like I said, we'll finish this next time. All right, so let's begin. So this is question number 9 from page 334. Now we don't need to do some of the questions. We're not going to do all of the questions because it might be a little bit tedious and kind of lengthy. So we'll do like parts of the questions because sometimes you don't need to do all of it because you kind of understand what's going on. So let's look at question number 9. Question number 9, you have 3 point charges that are 0.2 meters away, forming an equilateral triangle. Okay. So it will look something like this. 1, 2, 3. Okay. So each charge is the same. So they're all positively charged. They're all 4 times 10 to the negative 6 coulombs of charge each. And they're all 0.2 meters away from each other. Okay. So the lengths of the triangle are 0.2 meters. So it's an equilateral triangle, which we know then that means the angle is 60 degrees, right? So we're just going to do one because the answer is going to be the same for all 3 because they're all the same charge. So let's imagine we take it from the point of view of this charge over here. Okay. So what's the charge? What's the force that charge will experience? So we know it's going to be then the sum of the interaction with this charge over here. So this one, and it's going to be this interaction of this charge over here. So if we add those up, then you'll get a net charge that this one will experience. So let's look at, we'll call this charge 1, and we'll call that charge 2. And we'll call that charge 3. So let's look at the interaction between charge 1 and 3. So we're going to use Coulomb's law. Okay. So we know the constant is 9 times 10 to the 9. I'll just leave out the units. The same charge. And the distance between them is 0.2. I said I was going to leave out the charge, and leave out the unit, and then I put the unit in. Okay, so there you go. So K times the charge, because it's the same charge squared, over 0.2 squared. So that's going to give us a force of about 3.6 newtons. Now, because all the charges are the same and all the distances are the same, that means this charge would also be 3.6 newtons here. So this is 3.6, and this would be 3.6. So if we take it from the point of view of charge 3 or object 3, then it's going to experience a force from object 1 of 3.6 newtons to the right. This is repulsive, right? Positive and positive. Now it's also going to experience this force of 3.6 newtons, but that one is obviously on an angle. So we can actually figure out the components, because we know that this would be 30 degrees. So if we look at the force from, we'll call it 2 and 3, we can break down that vector into its components. So we know that's 30 degrees. So just using some basic trig, obviously opposite side is sine. So sine 30 times 3.6 would give you a force of about 1.8 newtons. And then cosine 30 times the hypotenuse will give you a force of about 3.1 newtons. So now if we add that up, we add the forces up, we can see we have, horizontally 3.6 newtons to the right from here, and another 1.8 newtons, because I can see that the vector is pointing down, but also to the right. So that will give us 5.4 newtons to the right. And if I look at the sum in the y, there's really only one in the y. That would be simply the 3.1 newtons heading down. So then that would give us a sum of 5.4 this way and 3.1 down. So then this, we know what to do. We do the sum of the squares. Well, if you do the sum of the squares, that would give you a net force of about 6.2 newtons. And because the distances in the particles are all the same, then each one experiences a net force of 6.2 newtons. Okay, is that okay for number 9? We can work out the angle, but I don't want to do I don't want to do everything in the questions because it's just going to take too long. The angle's easy, right? I think you should be able to figure that out. Okay, that's number 9, page 334. I looked at number 1 on page 343, and it seemed like a question to look at too. So number 1 is, and again, stop me if you have any questions, okay? So number 1 is you have an object that is negatively charged. You see the charge here, 2.4 times 10 to the negative 6 coulombs, and it's experiencing a force of 3.2 newtons to the left. So here's my object. We're going to draw it out. So here's my negatively charged object. And it's experiencing, it says has a charge of 2.4 times 10 negative 6 coulombs. So we're going to figure out the EF. All right, so that's the first part. Now it says it experiences a force to the left. So there's a force going that way. Okay. All right, so A, determine the electric field. So the electric field is the force per unit charge. Because remember, the unit is newtons per coulomb. So it's going to experience a force of 3.2 newtons to the left. And the charge is 2.4 times 10 to the minus 6 coulombs. So we could say then that the electric field would be 3.2 divided by 2.4 times 10 to the minus 6. So that should be 1.3? 3.2 divided by, what was it? 2.4 to the exponent 6 negative is 1.3 times 10 to the 6 newtons per coulomb. Now, the second part of the question is what would, so the reason why I picked this question is not because the calculation was hard. It's actually because of the follow-up question. It says what would the electric field be if we replace the charge with, so we replace this charge with this charge. And it turns out the electric field is still the same. Because the electric field is in reference to the object that is exerting or producing the electric field. So it's actually irrelevant in regards to the charge that we're placing in the electric field. So it would be the same. What would be different would be the force experienced by the particle. Because this particle has a greater charge, it would therefore experience a force. In this case, it would be double the force because it's double the charge. All right. Are we okay with that? Okay, so let's look at number 3 on page 343. So number 3 on page 343. Calculate the electric field in direction 3 meters to the right of a 5.4 times 10 to the minus 4 charged object. Okay, so so again, the electric field would be so if you remember, there's another way we can get the electric field. We can calculate it as K, Q, Q source. Wait, hold on a second. Wait, 1 second. Hold on. I think, is this the right question? Let me just double check something here. Yeah, okay, it is the right question. Okay, all right. So we can calculate the electric field as a function of KQ1 over R squared. So in this case, we could say that, you know, the electric field would be 9 times 10 to the 9 times 5.4 times 10 to the minus 4 over R squared, R being 3 squared. So the electric field would be 5.4 times 10 to the 5. And we know what it is. It's newtons per coulomb. Now to the right of, so if the charge is, so if this is my charge and we're talking about the right side, then the direction would be away. Okay, or we can say to the right. So you would experience the electric field heading this way. That would be the direction. Okay. All right. So next question. That was number 3, page 343. Okay. So let's look at number 1, page 354. Determine the charge if the voltage is minus 6.4 times 10 to the minus 4 coulombs at a distance of 25 centimeters. Okay. I think that's supposed to be voltages. This is supposed to be voltage, not coulombs. Let's make that adjustment. All right. So what's the charge? Okay, so if you remember, we could work out, so let's say write down our variable, what we have here. So we have the voltage, minus 6.4 times 10 to the minus 4 volts, which is the same as joules per coulomb, or volts. We have our distance of 25 centimeters, which is 0.25 meters. If you recall, we could measure voltage as voltage is KQ over R. So in this case here, we can get the charge. We could rearrange for that and say Q is VR over K. So the voltage would be 6.4 times 10 to the minus 4 joules per coulomb. I'm gonna leave the units out because you know what, you're gonna end up with coulombs in the end. Times the distance, which is 0.25 meters over K. It's 9 times 10 to the 9. Okay. So that will give you a charge of about 1.8 times 10 to the negative 6 coulombs. All right. So that's number 1, page 354. Girls, are we okay so far? And there's a lot of equations in this unit, aren't there? There's a ton of equations in this unit. Okay, so let's the next, so on page 354, I was looking at the questions, and number 3 and 4 are quite similar, so I just picked number 4 to do. So we're going to do number 4 right now. Let me just double check to make sure the question's correct. Yeah, this is the right question. 2 parallel plates, 1.2 centimeters apart, and the electric field strength is 1.5 times 10 to the 4. Just double check and make sure the numbers are correct. Okay, so we're going to figure out the voltage in number 4. So if you remember, we could measure the electric field. So it says the electric field is force per charge. So that's what you have here. But if you recall, we can also measure the electric field a different way. We could say the electric field is the voltage over the distance. They actually work out to be the same thing. So in this case here, we're looking for the voltage, so we could rearrange and say that the voltage is the electric field times the distance, which is 1.2 centimeters, but you gotta make sure that's in meters. And you know, if you remember, newtons times meters, a Newton meter is a joule, right? So that's why they're equivalent. So that would give you a voltage. What is that? 1.5 to the exponent 4 times 0.0, was it 002? 0.02, 0.012. It's 180 volts. So this would be 180 volts. Okay. All right. Our question? Oops. The previous question is minus 14. Is it minus 14 in the question, page 354? Number 1? Sorry. Oh, for the answer. Oh. Yeah, that would make a lot more sense. Yeah, that would make a lot more sense. That could be minus 6. It should be minus 14. Correct. Very good. Yeah, because minus 4 divided by 9 right there is already minus 13. So that would make, thank you. That would make a lot more sense. Okay, so minus 14. Thanks. Thank you. Yeah, that would make a lot more sense. Okay, yeah, if you notice any mistakes, please just jump in. I don't want you had the wrong answer here. Okay, so what's number 4? Let's look at number 8 now. Number 8, page 359. This one is where we're looking at. So I came across this question. I didn't actually assign this question. It wasn't part of the course outline, but so maybe I should have assigned it because it's actually not explained. Like it's not explained that well in the book. So maybe we should, look at this question. So let's take a look at it. Number 8 on page 359. You have 3 objects. Now we'll just do one, just to show you how to do it. You can do the rest because the method's going to be the same. So let's say I have 3 objects like this: 1, 2, and 3. Okay. And let's say that this object is, actually I want to make sure that the charge is in the right spot. So this one I'm going to draw, you see in the actual book, okay? So in the book, you have an equilateral triangle like this. And each side is 2 meters long, okay? Now, this charge is plus 4 microcoulombs. This charge is 2 microcoulombs. And this is minus 4 microcoulombs. Okay. So the question is, if you had a point in between, so let's say we picked, for instance, this point. Okay. What would the voltage be at that point? Okay. So in a question like this, the way you do it is you add up the voltages, and then you will get like a net voltage that thing or that point would experience. So for instance, we have 3 point charges that are a particular distance away from this point, okay? So we're just going to call that point A. So we know the voltage can be calculated as K, Q, source over R. So point A, if we add up the voltages from the different points, so this point source, call it 1, call that one 2, call that one 3. If we add that all up, then we could determine the voltage at point A, all right? Now, voltage is actually a scalar quantity, so there's actually, you don't need to worry about directions, but the sign obviously is going to be important. So we are going to just simply add up all the voltages. So the voltage as experienced in relation to charge 1 would be K, so 9 times 10 to the 9, times 4 times 10 to the minus 6, and it would be 1 meter away. Okay, it would be 1 meter away. The other object, call it 2, so this is from 1, would be 9 times 10 to the 9 times 2 times 10 to the minus 6, and it's also 1 meter away. Okay? Now, the other object is not 1 meter away, right? I mean, it's obviously going to be a different distance. Well, we can work that out. We know that that's 1. We know that that's 2. So this should be root 3. That should be the length of that from point A to that charge number. We'll call it charge 3. So we could work out that value as, but it's negative. This is a negative charge. So when we add it up, it's actually going to be a negative value. Okay. Oop. Oh, what happened there? Just disappeared. Times. Oh, I know why, because I'm at the edge of my screen. So it's, okay, let me just slide over a little bit. Give myself a bit more room here. So minus, or how about we do this? Just so we keep it consistent with the charge. So plus 9 times 10 to the 9 times negative 4 times 10 to the minus 6. So we know it's going to be negative anyways, over root 3, which is about 1.7. Okay. So just to save you some time, we add it all up. That would be 3. This is about 3.6 times 10 to the minus, 10 to the 4. This is about 1.8 times 10 to the 4. And this is about 2.1, sorry, negative 2.1 times 10 to the 4. So if we add that all up, that would be around 3.3 times 10 to the 4, because 3.6 and negative 2.1 are about 1.5, plus 1.8 is about 3.3 times 10 to the 4. So that point, this, we'll call it A, would experience a voltage of about 3.3 times 10 to the 4 volts. Okay, and you would do the same method for this point and then for that point. Okay. All right. Okay, let's move on. Let's look at number 2, page 364. The next couple of questions actually are kind of similar to your milk and oil drop experiment. So this is page 364. Let me just double check to make sure that the numbers are right. The mass is 4.3 times 10 to the negative 9, and the electric field is pointing up, and it's 9.2 times 10 to the 2. Can we do number 1 on page 364? Okay, so if one has a charge of minus 3Q and the other one has a charge of 5Q, and then they come in contact. So they're going to reach some sort of an equilibrium after they come in contact, which I would imagine if we do the math, there's a overall charge of plus 2Q. So I think after they come in contact, each one would be plus 1Q after they come in contact. Now, if they're separated by a distance of 1.5 meters, and the force, find the number of electrons. Okay, so let's see. So they're going to have the same charge. So we can say Q squared would be F3 times R squared over K. So it says the force is 8.1 times 10 to the minus 2 newtons. All right. The distance is what did it say it was? 1.5 meters squared over 9 times 10 to the 9. Okay, so what is that? So the electric force is, what did I say it was? 8.1 times 10 to the minus 2 times 1.5 squared times 1.5 squared divided by 9 to the exponent 9. Now that's Q squared, right? That's Q squared. So Q squared is going to equal 0.00. Okay, so if we take the square root of that, so Q is 0.000045. So let's say Q is 0.0000. How many zeros were there? 4? 5. Okay. 4, 5. So Q would be 4.5 times 10 to the minus 3, 4, 5, 6. So it's 4.5 microcoulombs. And then to figure out the number of electrons transferred, okay, so if this is 1Q, I guess we could say that to go from minus 3Q to plus 1Q, you had to change it by 4. So 4Q. So that would be, there's something. Okay, so then that would represent 18 times 10 to the minus 6 coulombs, which is 1.8 times 10 to the minus 5. So now we could figure out the, we could work out then the amount of electrons. Because the charge is number times the elementary charge. So E would be Q over, sorry, N. N is Q over E. And the elementary charge is coulombs per electron. What was it again? 1.8 times 10 to the negative 5. Oops, I don't know. Why does it do that? 1.8 to the exponent 5 negative divided by the elementary charge. So what is that? I'll say 1.1 times 10 to the what? 6, 9, 12, 14. So it ends up being 1.1 times 10 to the 14 electrons. Is that what the answer in the back of the book is? Okay. Okay, good. All right. Well, that's a hot mess here, all over the place. Okay. All right. Okay, so let's go back then to number. Oh, we still got a lot to do here. Okay. Whew. What do you want to do one more and then we'll finish up? We got quite a bit still here. What do you want to do? You want to just finish these up, or do you want to? Let's see how far we get. Okay, that's number 2 on page 364. So this is a small drop of water, mass 4.3 times 10 to the minus 9 kilograms, and it's suspended. So what that means, if it's suspended, that means the forces are balanced on it, right? So if this is our oil droplet and it's suspended between the two plates, that obviously the electric force and the gravitational force are balanced. So the electric force must be pointing up because gravity is pointing down. Okay, so now it says the electric field is pointing up. So if the electric field is pointing up, that tells us the bottom is positive and the top is negative. Which means then that the obviously the water droplet has to be positively charged, right? Because there's a repulsion with the ground. Okay, so it's obviously going to be positively charged. So what is that charge? Okay, so the forces have to be balanced. So here's what we know. We know that Fe equals Fg. We know Fe is K. Oh, we have the electric field there. We don't need to do all that. We don't need to do all that. So if you recall, we can define the electric field as the electric force over the charge, which means we could say the electric force would be simply the electric field times the charge. So now we can actually plug that into here. So we could say that the electric field times the charge would equal the mass times g. We can then rearrange for Q and say mg over EF is Q. So Q would be the mass. So 4.3 times 10 to the minus 9 times G. The electric field, which is 9.2 times 10 to the 2 newtons per coulomb. Okay, so that would give us a charge of about 4.7 times 10 to the minus 11 coulombs. If you want to know how many electrons that is, like we did last time, so Q is Ne. So the number of electrons would be Q over E. So that would give us 4.7 times 10 to the minus 11 coulombs over the elementary charge. Oh, again, I hit the edge of the paper. Okay, so N would be about 2.9, close to 3 times 10 to the 8 electrons. Now, these are electrons that have been lost because it's positively charged, right? So it would be a deficit of electrons. Okay, so do you want to just do the rest, or do you want to finish these off on Tuesday? Because we still got 1, 2, 3, 4, 5, 6. That's still quite a bit. Should we just finish them off on Tuesday? When I click the chat, I don't see anything until I have to double click it. Tuesday. So let's, do you want to finish it up on Tuesday? Tuesday? Okay. Yeah, let's do that. Let's just split it up. Because that's still 6 questions to look at. Okay, let me stop the record. Hold on.